digital fabrication and really specifically how it relates to personal fabrication. But before we talk about that, let's talk about the past. So let's go on a little detour through history. This is the ENIAC machine. Actually, where are you guys looking? Over there. Which was one of the first digital computers, which was developed in the 1950s as part of the Cold War effort to be able to calculate missile trajectories and artillery firing tables. So not exactly the most peaceful thing to be able to do. But it was a pretty cool technology. Computing things is useful. And quickly it was readopted and changed to be a personal computer. So no longer war machines, but now something that was more relevant to personal computing. And so here's a metaphor that maybe we can leverage for digital fabrication. If you can go from a digital computer to a personal computer in 25 years, can you go from digital fabrication to personal fabrication in 25 years? Not exactly. We haven't exactly followed the same trajectory. And the question here is, why not? This is one of Apple's factories. This is a factory in the Pacific Northwest that makes Mac Pros. And so Apple is a big company that has access to the kind of technology you might use for digital fabrication, such as CNC machines. And yet they use it to make all of these exactly the same product, maybe 7 different products at a time. And so even though you can recode any of these machines to make anything different at any given time, they're actually using these machines which could be used for low volume production for mass production. And that's good for them because when you make something with the aesthetics of low volume production, it has kind of implications of luxury and expense, which is good for their brand, but doesn't necessarily leverage the capabilities that CNC machines give you. If I wanted to change the code and change what kind of machine or what kind of enclosure I was making with these machines, that would be very easy, but they don't necessarily do that. And so it is, we're working on factories of the future. There's a program that we've been working on with Philips, for example, to figure out how to do low volume production of lots of individual and different kinds of products at any given time. And one of the big champions of this kind of factory of the future vision is everyone using these reconfigurable robot arms, which are very smart and fancy and cool. So this is, for example, Universal Robot's robot arm. It not only is position controlled, but also force controlled. So not only can I tell it to move somewhere, but it also won't necessarily kill you when it crashes into you because it knows how much force you're applying. And you can put different end effectors at the end of this robot. So you can configure this robot to do different kinds of things. And you there is this sort of ephemeral, technologists, can do anything at any time. Well, I am a technologist. I work at MIT. And here we have a different robot arm, a KUKA robot arm, that we're using to cut this is at the end of this robot arm, there's like a hot end that's cutting a complex surface out of styrofoam that's going to be cast into like a multiple curvature wall surface to build up an architectural model, which is going to be very fancy. And the way that you interact with this robot is you create a model, and then based on the model, you create a toolpath, and based on the toolpath, the robot moves in a certain way. But the calculations for how the robot's joints have to move, they're always kind of different and a little bit complicated. So there's some magic that happens there, and then there's other magic that also happens when you have to figure out what that end effector specifically needs to be doing at that time. And so in this case, these students thought it would be too much work to actually develop the electronics for this particular weekend hack to do the temperature control of this hot end. And so instead of actually making a controller for it, the guy that's standing on the left is holding a surge protector, and he's flipping the switch off and on to control the temperature. And so not so AI, very much human intelligence for doing one of the most simple control loops that you could possibly imagine. So that's kind of too bad. So it looks like we're supposed to have this really, bright future of reconfigurable robots running all of the factories of the future. But actually, a lot of these tools that we're developing don't necessarily meet the needs of the people who need to reconfigure them actually to do low volume. If you're Apple and your idea of low volume is 1 million units a year, then okay, you can spend a week doing the startup in which you program the specific toolpath that you need for your specific product. But if you want to make 10 units or if you want to make 100 units, you don't have time for that kind of investment. And so this metaphor that I want to use, where we're going from digital fabrication to personal fabrication as we went from digital computation to personal computation, isn't exactly holding. This is a milling machine at NASA Ames, where other collaborators of ours work. And this milling machine is a very nice milling machine. This is the one that mills things out of titanium that then go up into space. And so this is what we think of as state-of-the-art fabrication, or this is something that can make really nice products. And yet, this is actually the same milling machine that they used in 1952 to hook up to the first digital computer the first time they tried to use a computer to control a machine. And so we haven't really gotten that far since. And so how can we think of making the infrastructure that we use for fabrication technology to be more expressive and useful for low volume production? And we're trying. So one of the things that my research group has spent a lot of time working on is Fab Labs. There's one here in Amsterdam in the Waag. And you can think of it as this one is in Iceland, in Westmeer. And you can think of it as the idea of, if you have digital fabrication tools, but they're kind of too expensive for individuals to use, then you can go to the equivalent of a library and use the tools there. So if you don't have an extra 1,000 euros lying around to be able to buy a 3D printer, maybe you can go somewhere else and use a 3D printer in the equivalent of these libraries. And to be able to make it more accessible, we've done a lot of other kinds of work, like rewrite all of the CAD/CAM software to make it more easily accessible by novices. But actually, I think that this is not really the answer. Like, this is educationally interesting, but if you look at what these tools can do in comparison to what a personal computer can do, if I want to do a calculation on a mainframe, then I can do that. And if I want to do the same calculation on a personal computer, I could do that too. It probably would just take much longer. But I wouldn't get a less precise answer, or I wouldn't get something totally different. Whereas if I try to fabricate something that I would make on the NASA mill in this Fab Lab, it would just not be possible. I don't have access to the same complexity or the same precision through these tools that I otherwise would if I did low volume manufacturing at a more expensive level. So I think that the problem here is that we think that maybe personal fabrication is too much like smaller, dumber, cheaper versions of industrial fabrication. And if we're going to make everything small, dumb, and cheap, then, well, that would be kind of a shitty world to live in, right? So in terms of the timeline that we're going through, if maybe 70 years ago we had the first digital computer, and more like 45 or maybe even 55 years ago we had the first personal computer, how can we go forward and what can we see next in terms of personal fabrication infrastructure? So I'm going to give you kind of some ideas of what I have been working on with some colleagues of what would it look like to have personal fabrication and not necessarily as a dumber, cheaper version of what we already have. But let's go on another excursion. So we went back in history for a while. Now instead of going back in history, let's go to China. This is a marketplace in Shenzhen that I like going to. These are all little booths where you can buy electronics, motors, things that you use to make machines. But each one of these little storefronts is a front to a factory. So if I want to go somewhere and say I want to buy a specific custom motor, or if I want to buy a specific kind of potentiometer or a different kind of actuator, I can go here and buy all of those different modules and reconfigure them into new products. And so often when we think about digital fabrication or the future of personal fabrication, people like to think about the Star Trek Replicator or some kind of beautiful white box vision of the future in which everything that we need is just kind of made for us without us really necessarily have to interact or intervene. And yet this model of the world, this kind of marketplace, is a totally different model where I can go here and pick different modules and reconfigure them into different things to create different kinds of technologies. And one of my favorite things to buy in this marketplace are these kind of shitty cell phones. This is a part of my collection of funny products that you can buy in these marketplaces. So on the left, for example, you can see my gold necklace Prashi dual SIM cell phone. On the bottom right, you can see an iPhone 10, and it's about half the size of an iPhone 5, and it runs Android. And there are all these different, none of these phones, like the Hermes handbag phone, which also has the Hermes operating system for running your phone, none of these are intended for mass manufacturing. Like, none of this is a disruptive thing that's going to scale and like make you millions of dollars. Each one of these has cheap enough cost of production that you can do something that's complex enough that it integrates software development, electronics development, and a hardware enclosure. Some of these are die-cast metal hardware enclosures. And yet it's cheap enough that someone can just be like, oh yeah, today I think I want to have a phone that looks like a pack of cigarettes. And so what if this kind of technology daydreaming that's taking place for phones, or something that they're comfortable in Shenzhen for manufacturing, because they're known for making everybody else's cell phones as well, if this is the kind of space that you can get of creativity and hardware remixing, what could we be able to do with digital fabrication equipment if we applied the same kind of modular marketplace creativity? So this is an idea that me and Alon Moyer had. It's a reimagining of, instead of you going to a library for personal fabrication, you could have something more like the laptop of personal fabrication. So this is it's a pretty old project, actually. So this is a 3D printer that pops up in this briefcase that you can carry around with you. And the head is interchangeable. And so here it's a 3D printer, but it can also function as a milling machine, as a liquid handler, as a cutting machine. It cut its own stickers that are on it. And it has this motion platform that makes it easy to move around quickly without necessarily moving a lot of the motor mass around. And so this was a prototype. And it was the kind of thing where people were like, oh, you should kickstart that. But actually, I think that more interestingly is this reimagining of what fabrication might look like if you took it out of the context that you normally think of fabrication tools in. So if this is something where I can make any circuit board that I need in the garden at any time, then what does that mean for how I intervene in the kind of electromechanical space around me? Can I make modifications all the time? And to be able to do this, we created a new kind of network control system, which was less like traditional machine control tools and more like robotics. So every time you want to on the fly modify something, so for example, the guys with the robot arm in the beginning that wanted to do temperature control, if they could have added another node to a network, which was a temperature control node, then they would have been able to have a control network that was easily adaptable to the problem that they had at hand, instead of having to design a whole new thing each time. And that might seem like kind of a technical distinction, and I'll talk much more about technicalities with anyone who wants to talk to me afterwards. But in practice, what it meant was that you can do much more rapid prototyping of these kinds of tools. Every time you need a new control system, or every time you need a different kind of machine, making the control system for it is as easy as prototyping the mechanics that go around it. So these are a bunch of different machines that I or students of mine developed, including liquid handling robots for biotesting and pharmacology, and a wire EDM for cutting high aspect ratio metal parts, a lot of different milling machines and educational tools. And yet, this isn't necessarily good yet either. So the Fab Lab wasn't that great because we have kind of dumb stuff that doesn't work as well. And now, as long as you're able to make a machine, you can make any machine you want. And so I can make lots of machines, but what about everybody else? It's not necessarily making this that accessible yet, or at least that's what we found working with all of these machines. So what if, besides making the network for the control system modular, we could also make the machine itself modular, or at least the motion components for them modular? So what if we started with something as simple as only 1 degree of freedom? So not a 6-axis robot arm, but just 1 degree of freedom. Or 2, where I'm moving something back and forth. Or 3, or 4. Like, what if this was the way that you could scale motion as well as control? And so this is kind of a project that I've been working together with James Coleman on, where we're using object-oriented hardware as a metaphor for creating lots of different instantiations of machines. And so if you can build up a machine out of lots of different modules, then each time you build a new configuration of a machine and you add a new end effector to it, you have a different machine. And if you don't necessarily want to make the product that you're making with that machine anymore, you take the modules and you reconfigure them to do something else. And if the modules are not sufficient, you just add another one, design another one, and add it into the machine network. So here's a prototype of that, where these are aluminum linear axes that we use to create a hot wire cutting machine. So this is also kind of an old prototype, but here are the network controls. My computer. And each one of these axes is individually addressable, but you can also create compound nodes, compound machine parts that you then address as one unit. So if I want to call an action on a whole instantiation that, for example, does 3-axis motion as well as temperature and position control, then I could do that. So here I'm doing advanced flight testing. Just kidding. And actually, for this particular machine, we at first made these. We just made this kind of configuration for this video. Oh, by the way, all of the design files for these machines are open source, and you can get them on that website, mtm.cba.mit.edu. And so the different configurations of these mechanical machines correspond to reconfigurable electronics. So networked electronics talk to network or reconfigurable and modular mechanics. But then there's also a software element, which I won't go into too much detail of, because personally I think software is so much less exciting than hardware. But one of the things that, of course, you need to be able to do once you've created a control system is you need to be able to call commands on the control system. And so to be able to call commands on the control system, this is a browser-based machine interface that we made called mods for modules. So each one of these modules can talk to either a component of the machine or several components of the machine at the same time, as well as do other kinds of things that you might need to do before you even called something on the machine. So this is all implemented in Node.js, and so you can, for example, take a video stream either from your webcam or from something slightly more fancy than that, and do some analysis on it and say, if the contents of this Petri dish turns from pink to blue and this blob shows up, then, shake the dish around and try to scoop out the contents of that blob. And that's the kind of prototyping that you really want someone to be able to do without necessarily understanding all of the internals of how the automation works. You want someone to be able to say, if Petri dish pink, then person very sick, like do something, and not all of the other things in between. And so this is also an extensible network modular software component to go with the firmware component to go with the hardware component, which I can tell you more about later as well if you want. So to make this all even more accessible, we decided that making the modules out of metal and having only people who had access to those modules reconfigure it was not necessarily scalable enough. And so we decided to make a version out of cardboard. Because cardboard, in a way, is like the ultimate modular material. It's not like Lego in that it's actually modular, but there's nobody that will be presented with a piece of cardboard and say, oh, geez, I really have no idea how to modify this. Anyone who wants to build a new kind of machine with cardboard can just cut it or glue different parts onto it. And so we made this cardboard construction kit for building machines that then was shared around the world in the class Fab Academy that we teach in Fab Labs. And these are some of the results of the machines that people made. So So the cardboard is laser cut, and that's because by bootstrapping the precision of one CNC machine, we can then harness that precision in the configuration of the next CNC machine. And so some lines are cut through and some are scored so that you can fold something together that is going to be highly rectilinear and easy to construct. This is the simple construction process. And so the idea is that a novice can make, say, 5 axes in a couple of hours, and then configure them to do all kinds of different things depending on what kind of machine they want to be building. And that's something that we thought actually worked really well. You had all of these novice machines. So here's our modular controls. There are a lot of people that made painting machines, a lot of people that made sketching machines, but this is a 3D scanner where they're moving the iPhone around to do kind of photogrammetry. Coffee stirring machine, because that's important. This is a kind of light show machine. But this, for example, is a 5-axis hot wire cutter. And so you have people that have never designed any kind of machine before who just go straight for 5-axis control, because software-wise, 5-axis control is actually not that hard a problem. It's just that once you end up dealing with expensive robots and things that might kill you, then you get kind of worried. Precision ketchup dispensing, precision cocktail mixing, and so I guess a lot of these machines seem kind of frivolous or trivial, right? You have all these kind of cardboard machines that are doing silly things like drawing or cocktail mixing. But if you're able to have frivolous machines that do precise things, then you can also make it easy to make serious things without necessarily a lot of upfront costs and buy-in. And so I think that this kind of techno daydreaming that you saw with the cell phones in Shenzhen, if we can apply that to digital fabrication as well and have everyone have access to, didn't mean to do that. And have everyone have access to the kind of precision and control that you have with digital fabrication, then I feel like we will be able to solve a lot more kinds of problems, a lot more kinds of technologies. No longer everyone with exactly the same laptop and cell phone, but people doing a lot of more local kinds of problem solving and solutions. Yeah, these are some of the most frivolous ones. This is a precision sand gardening machine. And not only did these people in Ohio build a precision sand gardening machine, but also these people in Italy. So it turns out there's a huge market for precision sand gardening. If anyone wants to start a company based on that, I recommend it. And so there are different, and just to, this is a workshop that we ran at SIGGRAPH, which is a computer graphics conference. So you really have people who are engaging with CNC who aren't already mechanical engineers or aren't already electrical engineers. And you have here someone who thinks, oh yeah, I want to modify this drawing machine to be a CNC milling machine. And now I'm just going to do that. I'm just going to tie wrap this Dremel tool straight onto this cardboard machine. And then when something goes wrong with that, then we're like, okay, maybe we should reinforce this with something more than cardboard. But that kind of frivolity in hardware production. So that was really what I wanted to share with you guys, and if you have any questions now, I'll take them.
So I have a question for you, Nadya. It looks like the type of work you're doing is, to make this kind of stuff more accessible to normal people. But it still seems like we're at the stage where, an object-oriented programming language is more accessible than machine code, but it's still not that accessible. So what do you think the biggest obstacle is before I'm going to be manufacturing my very own Hermes mobile phone in my house?
Right. Well, I think that there's kind of two sides to that problem. One side is educational, like how can we educate as many people as possible to be technological, and that part is important. But I also think that the kind of flip side to that is infrastructural. How are we making the object-oriented hardware analogy accessible enough in its implementation that education becomes less important because things are kind of self-explanatory. And I think that up until now, the biggest difficulty has been the people who need new infrastructures of fabrication are not the same people that need accessible fabrication. Like if you think about who does custom complex hardware prototyping, like the military, the healthcare industry, none of those people are like, oh geez, we want everything to be really cheap and easy to use. And so there's like a conflict by who's developing infrastructure for machine building and who's using infrastructure for machine building. And so the way at least that I like to approach it is, well, you know, the military funds us too. A lot of this cardboard machine stuff was funded by the military.
So you're a Trojan horse.
Oh yeah, totally. Or at least I think of it like kind of as judo. You're like, oh yeah, I'll take your money and I'm moving it in this direction.